All right, hey there, PCH. So for all of Unit 4 so far, we've almost exclusively focused on exponential functions. Haven't really touched on logs, but that's going to change right now as we're going to do some intro notes to logs. And so in order to get started, I really want us to focus on the question, what is a logarithm? And when we think about that question, our ultimate response is that a logarithm is an exponent. And that is such an important point to understand. I'm sure many of us remember that from last year because it's so important. And I will repeat it over and over again just to make sure that we understand that, again, a logarithm is an exponent. And now, why does that matter for us? And I want us to focus on these next two paragraphs to really think about that. For example, if someone came up to us and asked us, hey, what's 2 to the 4th power? I think a lot of us could easily say that 2 to the 4th power is 16. But what if someone instead came up and asked us, 2 raised to which power equals 16? And if we were to write that out as a function, it'd be something along the lines of 2 to the x equals 16. Now we know from experience, based on different problems that we've done this unit so far, that when we're trying to solve for a variable in the exponent, it causes some issues for us because it's not as simple as just solving for it. We have to get that variable out of our exponent. Logarithms allow us to do just that. And so you'll see, again, like we said, logarithms are exponents. When you're looking here, if we have 2 to the 4th equals 16, when we write it as a log, that exponent of 4 ends up being taken out of the exponent and being set equal to this log. That allows us to actually solve for this. And so, of course, in this example here, we get log base 2 of 16 is equal to x. Again, x has been taken out of the exponent, and that allows us to actually solve for it. And so the key difference, again, is that in exponential form, the power is isolated. What essentially equates to our y value is isolated. When we have something written in logarithmic form, our exponent is isolated. And that is going to be super helpful for us, as you'll see in just a few seconds. But first, I'm going to make sure we stamp this point one more time. A logarithm or a log is a what? You tell me. Yes, a log is an exponent. Nice job. Let's move on. Another fact that we're going to come to in a little bit, in a few lessons, is that logs and exponential functions are inverses of each other. I just want to put that on our radar so that when we come to it again in a few days, it will not be entirely new information for us. But when we are looking at the form of a log, we see that we have a few things going on. We have a variable b, an a, and an x. When we think about what those are, our b is our base, our a value is our argument, and our x value, of course, is our exponent. And keeping those things in mind, when we convert from logs to exponential form, we end up getting b to the x is equal to a. Our base, excuse me, to our exponent is equal to our argument. One way to remember that, if you are starting with logarithmic form and you're trying to convert to exponential form, is to use something that I like to call the chubby hand. And so we have b to the x is equal to a. You see this motion I made with my marker, it kind of looks like a chubby hand. And that helps us convert from logarithmic form to exponential form. And I want to point out one more thing when it comes to the formation of logs. And so, of course, when we have to talk about logs, there's a certain way that we say what's going on in order for people to understand what's our base, what's our argument, what's our exponent, things like that. And so when we are talking about a log, we always say the log base b of a is x. Great, let's move on to the two different types of logs that we know. Of course, the primary or most common log is the common log, and that's written with the letters log. Now, of course, like we just talked about, every log has a base. The common log, as it's understood, always has a base of 10 unless otherwise noted. And so if we're thinking about it, like in the form we just wrote it as, log base 10 of x is equivalent to, if you just see log of x. The base 10 is understood. The other type of log we know is the natural log, and that's written with the letters ln. Now, the base of the natural log is e. And so we have natural log base e of x. That's the same thing as the natural log of x, which is the same thing as the common log base e of x. Great. We've talked about a lot that has to do with logs, a lot of the information that we learned from last year. And so the rest of this lesson is just going to simply focus on converting between exponential form and logarithmic form, and vice versa, of course. And so, look at that, just in case you forgot, logs are exponents. Do not forget it. Again, so let's start with number 1 here. We are given log base 7 of 5 is equal to x, and we need to convert that to exponential form. I'm going to go ahead and use my chubby hand. So 7 to the x is equal to 5. 7 to the x is equal to 5. Perfect. Now we're given exponential form. And so what I like to think about here is, again, because logs are exponents, I know that I'm going to have something that is a log equal to our exponent in our exponential form. So something is equal to 5. Another thing I know is that if I scroll up and look at our notes again, the base in my log is the same base in my exponent, or of the base in my exponential form. And so when I look here, my base in my exponential form is 4. I know I'm going to have log base 4 of my argument, which is a, equal to 5. All right, I want you guys to do the next two. So we will start with this example here. All right, hopefully you were able to use the chubby hand, and remember that if there is no base written for a common log, it's understood that that base is 10. And so when I do my chubby hand, I get 10 to the power of z is equal to 4. All right, your turn to try on number 4. All right, similar to the previous example, our base was not written, but based on our knowledge of the natural log, we know that the base is understood to be e. And so I end up getting e to the power of 6 is equal to x. All right, we'll finish with a few more examples. So, again, if we think about us trying to solve for x, in order to solve for this, we can go ahead and rewrite it into exponential form. So we get 2 to the x is equal to 8. And we know this one's pretty easy for us. And so we know that 2 cubed is equal to 8. And so when we're evaluating this log, log base 2 of 8 is equal to 3. Same thing for number 2. If we want to rewrite this as 3 to the x is equal to 81, I'm pretty confident that 3 to the 4th power is 81. Okay, let's do one more example together before I send you off to do the rest on your own. So we have 5 to the x, which is what we're solving for, is equal to 1/25. Now, I know that 5 squared is equal to 25, but I see that my argument is a fraction. We know based on the exponent properties that we've been studying that if we have 5 squared equal to 25, 5 to the negative 2 is going to be the reciprocal, 1 over 25. And so when I think about solving or evaluating this log, my exponent is going to be negative. And I really want you to think about this here. When we have an argument that's a fraction, that's less than 1, our exponent, or when we evaluate this log, we're going to get a negative answer. All right. I'm going to go ahead and let you guys work on number 4 on your own. Okay, this one was a little bit more difficult, but if we rewrite it as 4 to the x equals 2, we know that the square root of 4 is equal to 2. And the square root written as a rational exponent is 1/2. And this is another thing I want to point out. Just like the last example, we had a special situation. In number 4, we do as well. What we notice here is that when our base is bigger than our argument, our exponent is going to be a fraction. It's going to be less than 1. All right, let's move on to number 5. You guys are going to do this one on your own too. When we rewrite this log, we get 9 to the x equals 1. If we have something raised to a power and it equals 1, always, 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 that exponent is going to be 0. And so, a third special situation. If our argument is equal to 1, our exponent will always be 0 regardless of what our base is. All right, try number 6. As you can see, for number 6, I got 3. Go ahead and try number 7 now. I hope number 7 didn't trick you, and I hope you're able to figure out that this log can actually not be evaluated. If we have something to a power equal to a negative number, like that's just not possible. If we have 4 to a positive number, we'll say 4 squared, we get 16. If we have 4 to a negative number, like 4 to the negative 2 power, that's going to give us 1 over 16. We will never have an opportunity or a situation where we have a base, like in this case 4, taken to a power, giving us a negative argument. That just will never happen. So that's another special situation. All right, finish up with number 8 and then we'll be finished. Okay, number 8 was a really nice one, and we see that we get the answer of 1 when we evaluate this log. And so, final special situation, when our base is equal to our argument, our exponent is equal to 1. All right, I said we'd be done, but I actually have one final question for you that's going to be some good thought for us going into our lesson on logs tomorrow. And so my question for you is, why does this matter? All right, I am excited to see what your guys' thoughts are on why we are even talking about logs in the first place. This is going to lead us into some really good discussion in our lesson tomorrow. See you guys then.